Okay, so here's where we left off last time. Still in partial derivatives. We talked about first order partial derivatives. We've talked about partial derivatives, right? Well, just like with single variable derivatives, where you can take a derivative of a derivative, and they call that a second derivative or a higher order derivative. Likewise, you can take higher order partials. And it's exactly what you would think it is. For example, you take this function f, you can take an x partial or you can take a y partial. Right? We've talked about the interpretations of those things. Various interpretations. Let me go ahead and, while we're on that point, remind you that it's important to make sure you understand all of the interpretations and the difference of context between those interpretations of partial derivative. Don't just decide, oh, this is the one I'm going to think of. That's how I'm going to think about it, and I won't use the others. That's not going to be sufficient. Excuse me. Okay, so having taken these partial derivatives, let's look, for example, at this x. Before we go on, another little bit of notation. Here's a notational alternative for partial derivative. We already talked about that one, right? It's kind of Leibniz notation-like, right? It's vaguely reminiscent of the whole df dx thing, but of course that little symbol. Very importantly, by the way, not a d. This thing here. That's not a D. It is also, very importantly, not a lowercase Greek letter delta. It's a new little symbol that's different from all of those. So just be aware of that. Okay, so the other notational alternative, as opposed to the Leibniz notation we introduced last time, is this. You just make a subscript of the variable with respect to which you're taking the partial derivative. And I'm going to call that vaguely Newton-like. Let me just remind you, in single variable calculus, we talk about, df dx, and then the alternative notation is to say f prime. Well, the idea is that the prime says, you're taking a derivative. Prime is sufficient in that context to say, taking a derivative. It's sufficient because there's only one input variable. There's only one variable with respect to which you could possibly mean take the derivative. And of course, in this multivariable partial derivative context, I could take the partial of this with respect to x, or I could take the partial with respect to y. So explicitly indicating the variable is sort of necessary in this. But other than that, it's, again, kind of vaguely, at least, sort of Newton-like. So, anyway. Okay, so those notations are both used a lot in different contexts. Okay, so of this x partial, we could take the x partial of that. Right? Or that same x partial, we could take the y partial of that. And it's just the same algebra, you just treat the other variable as a constant and take the derivative in the usual way. Okay. Another comment about notation, let's look at this one here, for example. Notice there's kind of a notational speed bump. Using the Newton notation, we took the x partial first, and then after that, after we took the x partial, we took the y partial of that result. In the Leibniz-like notation, let's see, let me write down, okay. We're taking f. If we do the x partial first, and then the y partial after that, notice that kind of suggests putting the partial x in the denominator on the right and putting the partial y in the denominator on the left. And notice that these seem to be in sort of opposite orders. Right? And it's just because, the Leibniz notation is sort of acting on the left side, and the Newton-like notation is sort of acting, at least notationally, on the right side. And so therefore, a succession of things seems to be in the opposite order. In both cases, notice, though, whichever one acts first is the closest to f. Whichever one acts second is farther away. So anyway, heads up about those little notational details. Okay, So we can take these partial derivatives. Now, notice, in a seeming coincidence, the y partial of the x partial and the x partial of the y partial are the same. Wow, weird. What are the odds? Random, right? And you can probably persuade yourself in this case it's just a monomial. You can see, look, the same numbers are going to come down. It doesn't matter which order those factors come down from the numerators, or from the exponents, excuse me. So pretty believable, but it turns out that this is true more often than you would sort of expect. In fact, it's usually true. With this one condition, if the function that you're interested in, if all of the second order partials are continuous, then you can show that this will always work. And good news, for vast collections of functions, the second order partials are continuous because the second order partials are the same kinds of functions that the original function was in the first place. So polynomial, for example. Well, all the partials are all polynomials, and we already know all polynomials are continuous, right? So trig functions, exponentials, all these functions, when you take their derivatives, you're going to get slightly different functions, but they're going to be made up out of the same kinds of functions. So it's really plausible, and usually the case, as far as we're concerned, that second order partials will be continuous, in which case it doesn't matter which order you take your partials. So that's a surprising fact, really. And I'm going to try to give you some sort of plausibility argument about it in a few minutes, but at first glance, certainly not obvious, right? In fact, I think even a little bit surprising. Okay. All right. So, what do they look like? What do these second partials look like? The unmixed second partials is exactly what you would think. Let's talk about these one at a time. Let's talk about this second partial with respect to x. So we're taking the x partial of the x partial. Notice that when you're taking the x partial of the x partial, the very first thing you're doing is fixing y. Y is not allowed to change. So we're looking in this cross-section of the graph. And having done that, we're taking a derivative with respect to x, and that's a statement about slopes of tangent lines. And then, with that second x partial, we are then, continuing to keep x fixed. In other words, we're still in that same cross-section, and then just taking a second x derivative, which means the same thing that it meant in a single variable context. We're looking at how those slopes change as you move in that direction. And you just get the same resulting idea. It tells you about concavity. Right, so the way I have the picture drawn here, this one example of a Pringle-shaped graph, geometrically, that cross-section is what you might call concave down, right? And the second partial is negative, correspondingly. Everybody on board? Real super believable, I think. I mean, it's exactly what you would sort of expect. Related observation about y partials. Here you're fixing x. We're going to set x equal to a constant and keep x constant for the whole time, and no surprise, again, it's a relationship to concavity. And just, for fun, I drew it where it's curving the other way this time, so it's concave up as you're looking in the y direction, and second partial with respect to y, positive. Okay. All right, here's where things get a little weirder. We just talked about geometric interpretations of this and this. But what about that mixed partial? What about that mixed partial? What does that look like? And you cannot just say, it's going to be kind of like it was in Calc 1, because it isn't. In Calc 1, there was only one variable. The green checkmark cases are like that because, in effect, in those cases, there really is only one variable, right? But if you look at these purple question mark cases, here sometimes x is constant, sometimes y is constant. Sometimes x is the variable, sometimes y is the variable. It is simply not the case, looking at these two, trying to make geometric interpretations of these two things. Simply not the case that there's only one variable. So no particularly evident analogies to single variable calculus. So we're in new territory here. Here's the way I like to think about it. It's suppose we're taking an x partial of a y partial. The idea is to take geometric interpretations of these partials, but different geometric interpretations of these partials. So we'll think about the y partial in the way that, we're kind of sort of most familiar. Namely, let's think of that y partial as indicating a slope of a tangent line in the y direction. That's what y partial is, right? Let's not think of this as being slopes of tangent lines. Not going to work out well if we try to make that point of view. Let's think of this x partial as how fast does the thing that I'm taking the derivative of, how fast is that thing moving as I move in the x direction? Now let me just remind you, that's a very different interpretation, right? So slope of a tangent line, when you're looking at a graph, sure. But then we have this completely different interpretation if you're taking a partial derivative, right, and you're not looking at a graph. If you just want to think about, what happens as I move in that direction, well, it's just a different point of view on partial derivatives. Okay. Alrighty. So I'm going to try to draw a picture of this now. Correction, I'm going to point to where I tried to draw a picture of this. And it's hard to draw these pictures because it's three-dimensional. The paper's two-dimensional. It's just intrinsically hard, right? But, I think we can make a reasonably good picture. So, partial with respect to y. Right, we're going to look then at a slope of a graph in the y direction. Right. By the way, notice I didn't draw the surface. I came to the conclusion that just makes the picture kind of harder to understand. We'll talk about what the surface might look like in just a moment. But here you might imagine is a tangent line to this graph that we're trying to understand. Tangent line in the y direction. Everybody on board so far? Okay. So what we want to get our hands on then, what this mixed second partial looks like is the idea of how does that slope in the y direction, how does that change as I move in the x direction? So, well, as you move in that x direction, at each point along the way, not just here, but as you move, right, at each one of these points, you can draw slopes. Well, looks like I didn't copy those very well. They might be different slopes as you move along. As you move in the x direction, the y direction slope will be changing. And if you draw a few of those, starting a little further back, and again, as you move along in that x direction, these slopes might change something like that. And now, being as this is again two-dimensional, real hard to visualize, I'm going to try to do a little literally hand waving to help you visualize what's going on here. So pretend like my hand is the slope. Let's see which way are we going here. So we're coming out of the, okay. So my hand here, right, represents that back slope like this, right? And the idea then, try to visualize what kind of a surface would do this, but that sort of a slope on the back end, as I move this way, the slope needs to go more like that. Okay, so as I come that way though, so here's what it kind of looks like. Everybody see what I'm doing here? Okay, so what does that looks like? It looks kind of like a triangle, honestly. There's a weird sort of bending. If I had, and unfortunately I don't, if I had a sheet of rubber or something, it's like I'm taking the sheet of rubber and on this back side, it needs to tilt this way. On the front side, it needs to tilt like that way. So imagine what would happen to a sheet of rubber if you kind of, and again, paper doesn't work very well, but if you tilt it that way on that end and this way on that end, just imagine literally doing that. And you're going to get this kind of saddle-looking sort of shape. Everybody see what I'm talking about there? It's really hard to draw, right? Okay, so that's what this mixed second partial is measuring. Something kind of like that. It's It's a kind of a twisting of the surface, and you can see the twisting again in how you're doing this. You're putting a twist on the surface. Okay. So anyway, there is no analog to this in single variable calculus. It's a new concept in a new context. Okay. All right. Okay. I've made the observation already at the start of Friday's lecture that partial derivatives are really, really useful for a lot of things. They're super easy to compute, and they're super relatable. And that's nice. It makes them a good sort of starting point from at least a certain point of view. And I did also say that, well, there's downsides to partial derivatives. They're very kind of elementary sort of things, and there's something fundamentally awkward about them. I'll talk more about that a little bit later on. But I will recognize that they are extremely handy for writing down really complicated things that have to do with the physical world. So, for example, here's a bunch of equations. These are all kind of physicsy, engineering sort of things that we're not going to talk about in this class, but you might see in future engineering classes if you take such. And notice everything in here is made up out of partial derivatives. The partial derivatives everywhere, right? Second partial here, second partial, first partial, just partial derivatives everywhere. By the way, this notation here, this little triangle like that, pointing end up, by the way, very important for that particular symbol, means the sum of the straight second partials. It's just a notational thing. So this is a bunch of partial derivatives as well. And in particular, let's talk about what these equations talk about. So Laplace's equation here. This is the equation that describes how electric potential voltage works. If you have charged particles placed around in various locations, there's going to be different voltage levels at different places nearby those charged particles. Well, how do you figure out what those electric potentials are at points in space in between the particles? Well, that's a very hard problem. And it is answered by coming to understand Laplace's equation, which is written in terms of partial derivatives. How does heat flow? I don't know if you ever thought about that, but suppose you have an aquarium, right? Glass aquarium full of a bunch of water, and suppose the water's not moving, right? Everything's sort of fixed. If you want to think of it as being an aquarium full of Jell-O, so it can't move, right? That works. And imagine that somebody puts a heat source in the bottom right rear corner of that aquarium. Well, that heat source is going to make it real hot around there. But it's all that heat is going to propagate through the Jell-O, water, whatever, right? And eventually it's going to be warm way over here at the opposite corner. It'll probably never be as warm there as it is down here, though. But the point is, heat's going to move over time. How does that work? Exactly how fast does the heat move and in which direction? And does it move in a straight line, is it kind of an exponential sort of movement, or what? There's a lot of details to understand there, and it's very complicated, and it is described by the heat equation, which is written in terms of partial derivatives, et cetera, et cetera. How do waves move? What's the deal with quantum mechanics? And there's a lot to say about that of course I'm not about to touch. But these are very important questions about physics and engineering, and the relevant equations are all in terms of partial derivatives. So no surprise, partial derivatives are extremely, extremely useful, and I just kind of wanted to point that out. Okay, you're not responsible for any of these equations, by the way. I just wanted to show them to you. Okay, next section. I guess I can zoom back in. So I want to remind you of some terminology from single variable calculus, and in fact you might not have seen at least one of these words here, but we're going to use the word here, and so I want to make sure that we're all on the same page terminologically. And so here's a picture that we consider in Calc 1 classes. Right? You've got some graph, and at some point, talk about the value of the function at that point. Call that A, for example. Right? And then you can look at a nearby point. I'll say X. Yeah. Right? You can say, I'd like to know, given what I know about what's going on at that point, I would like to figure out what can I conclude about what's going on at that point. Right? And y'all remember, of course, the standard move that you do is you draw the tangent line and you make an argument about how the slope of that tangent line is the derivative of the purple function at that point A. Right? And then you can, make various calculations. So a couple of items of interest on here. There are two items of interest that I want to talk about. First is what I will call the increment. This book calls the increment. And it's the difference in the value of the function here versus the value of the function there. So the increment delta f is that right there. We're going to use the word increment. As y'all know, we approximate the increment by way of looking at the linear approximation. And we draw this little triangle here. And what we can compute is this thing called the differential. How much does our linear approximation change? So understanding only the derivative at this point A, we can compute this estimate of the increment. The differential is an estimate of the increment, right? Only knowing the derivative at this point, we can't actually compute the increment itself, but the differential is something that we can compute, and it's depending on the circumstances, sometimes a reasonably good estimate. Okay, so this is all Calc 1, and I hope you all remember this stuff. Is everybody on board with that? Okay, so that reminded. Let me remind you also that we have this formula here for linear approximations. This is a linear approximation of a function of two variables. Okay. Everybody remember this? Where did this function come from? This is the unique linear function that mimics f in value and in both of the partial derivatives. This function's got the same value as f at a. It's got the same partial with respect to x at a, and it's got the same partial with respect to y at a. It's a linear ripoff of the original function. Okay, yeah, everybody good? Okay, so, well, this being our linear approximation, the difference between the starting value and our linear estimate of the ending value, there's our differential. Oh, here, let me use colors consistently. We'll use here. So this difference gives you our differential, df. So df just says that's our linear estimate, using our linear approximation, our linear estimate of how much the function's changing. And we have a formula for that, like so. Right? Now, how close was it? I don't know. That's a harder question. But that's what our estimate is. So this is analogous to this thing here in single variable calculus. Right? Okay, so differential. Now let's rewrite this a little bit. You just kind of notice that is in fact a dot product. Look at this. It's that and that multiplied by that and then added. Right? That is exactly the structure of a dot product. So we have in fact that vector dot that vector. Now that's just an algebraic coincidence, it would seem. Certainly that doesn't prove anything. That's just, hey, look at that. It's kind of a alternative way to write the same exact formula for this differential. Now I will point out though that this thing here is a pretty natural thing to talk about. X minus a, y minus b. Remind you what our picture is. We've got some domain here. We've got some point here, a comma b, and some point over here near which we want to estimate the function x comma y, and the function's got real values and it comes over that way, let's say. Right, so looking in the domain, x minus a comma y minus b, that vector, that is the vector x minus a. The vector x minus the vector a. You know? So, in fact, in the same sense that we might call this dx, and you all probably remember dx referring to a, how much are you changing on the x-axis? So x minus a can be rewritten as dx. Along those same lines, this thing here we will rewrite as the dx vector. How are we doing? Everybody happy? Okay. All right. So here's what we got. This thing that we're interested in is a very natural construction, namely dot product, with a very natural item, namely the input differential, dx. Right? And the fact that something we're interested in is very naturally related to something else that we are interested in makes this thing intrinsically interesting. Right? It is unavoidable. It is the thing which, in a very natural way, relates these two other very natural things. Therefore, it's an interesting object. Yeah.
What is like the upside down triangle?
Oh, I haven't gotten there yet. Yeah, it's just notation. I'm seconds away. But let me just make sure we're all clear. I mean, the reason we're interested in this is because of, in this seeming coincidence, we have this very crisp connection between two obviously interesting things, and therefore that thing I have circled in blue, I've raised an eyebrow, right? I mean, it's just got to be interesting, yeah.
Is df the same thing as lx?
No, df is the differential. Yeah, df is the difference between these two things. Okay. It's L of x minus L of a, okay, which of course is the same as f of a. Okay. Yeah, right. Okay. So this thing, an interesting object, and we're going to give it a name. We're going to study it more later on. For the moment, we're just going to call it interesting because, look at it, fits in algebraically in a wonderful way. We're going to give it a name. We're going to call that the gradient of the function f at the point A. We use this notation. This is an upside down triangle, you might call it. Very importantly, the vertex down. It's really important you don't get that confused with this one where the vertex is up. They mean very different things. So we're going to be doing almost nothing with that notation in this class. We're going to be doing lots and lots of things with this notation, vertex down. Okay. All right, so it's called the gradient. Again, we give it a name and a notation because, check it out. It's really interesting how it fits in like that. There's much more to say about it, and we will say that stuff later. So with all of that having been decided, here's what this formula turns into. This formula turns into this formula. And that's really a very elegant formula. If you think about it, it's very elegant. What we have here is an input change and an output change, right? Our linear estimate of the output change. By the way, where have we heard that before? One of the first things I said about derivatives in this multivariable context, right, is that all of the derivatives we're going to talk about in this class are relationships between input changes and output changes, right? And what we have here in the form of this gradient vector is that is the thing that allows you to take an input change, dx, and get our estimate of the output change, df. Well, in a single variable context, the thing that's the relationship between input changes and output changes we call the derivative. So we have ourselves here a new kind of a derivative, and this is extremely naturally meaningful to think of this thing, the gradient vector, as being the derivative of this function. Right? Now, in a different way, the partial derivatives, okay, if you assume you're going to sort of unnaturally and arbitrarily, I'm going to hold all these other variables constant, they're not allowed to change this, in this weird construction where I'm really trying to force it I'm trying to cram this multivariable context into this very limited set of previous experiences that I have from Calc 1, trying to make it fit, and I can come up with this idea of partial derivative. This, I didn't have to cram anything, right? We've got a multivariable function, input changes, output changes, there's the relationship between them. That is arguably more naturally a derivative than partial derivatives. I'm a pretty big fan at this point. This is not a minor point. So anyway, I think that's pretty darn neat. And heads up, we're going to be doing a lot of stuff with this thing. By the way, this is not the only other derivative that we're going to talk about in this class. There's another one coming. And we'll get to that later. Okay. All right. By the way, I did this analysis for functions of two variables, kind of arbitrarily. If you write it down for functions of several variables, it goes through pretty much the same way, and you still motivate the same idea of a gradient. The formula for the gradient is still a vector whose coordinates are simply the partial derivatives of the function written in order, just like in this case. Okay. Alrighty. Okay. So let's take advantage of this formula. Let's just make get our hands dirty, make a quick use of it. And by the way, y'all remember back to Calc 1, we used this formula. Well, okay, I didn't write it down, but we used the formula for the linear approximation to given some algebraic expression that you can view as being the value of some function. Let's try to estimate the value of that expression, and we estimate by picking a nearby base point where the calculation is easy, and then we do our linear approximation and compute our differential, and the original easy to compute value plus our not so bad to compute differential gives us our approximation of the actual value that we're looking at. So this is just going to be a multivariable version of that. Same basic idea. Here we go. Suppose I want to estimate this nasty little expression here. Right? So yikes. Okay, I'll make the observation. That is what you would get if you plugged into this function, if you plugged that point. Well, not quite, but pretty close. Let's just think that through. If you plugged in this value into x, right, and if you plugged this value in for y, pretty close. It's not quite. I mean, it's supposed to be 3.02. Supposed to be 3.02, not 3 even, and it's supposed to be 0.01 instead of flat 0, right? But those values are not that far off. So, and what's great about this argument, this observation that we can look at this function at that point, is that arithmetic is easy. Plug in x equals 3, plug in y equals 0. Easy arithmetic, and it's just 2, right? The calculation's casual observation, easy to do. Okay, so this is our nearby base point. This is not exactly the point where we want to evaluate the function, but it's really, really close, and it's really, really easy. Okay. All right. Now, again, not exactly where we want to be. We really want to be a little further over. So this plus that would give us the correct value of x, the correct value of y. That would actually give us the actual value we're interested in. Okay, so this is, we've got our setup done. We want to estimate the value of this function using that as a base point and using that as our dx. Plug into the formula on the previous page, right here. Right, dx is right there. The dot product. Now I am going to have to compute the gradient vector. Don't forget the gradient is made up of all the partial derivatives. So I am going to have to do a little work on this. I'm going to have to take this function and take a couple of partial derivatives like that. That gives me this. It's just partial derivatives. Make sure you can do that. Right? By the way, notice in doing these partial derivatives, I'm also pointing out that you have to be able to do single variable derivatives, right? So make sure you remember all your chain rule stuff. And this example doesn't have product rule, quotient rule, but make sure you know those as well. Again, that's going to be assumed that you are just slick, proficient with all that kind of stuff. Okay. All right, so I've got an expression and kind of crank it out. Now there's one last question to point out, and that is, okay, well, isn't this problem here, I'm going to have to evaluate these expressions here, and aren't they just as hard as that expression? And, well, very importantly, no. Very importantly, into these expressions here, we plug the base point A, right? Look back up here. All of these partial derivatives are evaluated at A. The gradient is then evaluated at A, because that's how linear approximations work. Right, we do linear approximations by understanding how f is changing at the base point, and then we extrapolate with those partial derivatives at the base point. We extrapolate from there. So these calculations are really easy. Again, we get to plug in the easy point there. So a little bit of arithmetic. The gradient turns into that. Make sure you can do that arithmetic. Right. Dx is still this. And we've got a really easy dot product to do here. Crank out that dot product, and it ends up being that right there. There you go. And that's our differential. That's our df. Now, don't forget the df is not what we were actually interested in. What we were actually interested in was the value. We just computed the differential. We wanted to know the value. The value then is, well, it's the original value plus the differential. The original value was just 2. Right, yes?
Where did you get your dx from?
So that's from... so we made a discussion about that where, the idea is that I'm interested in a point that's kind of the sum of these, and I like this point because it's easy, but what I actually need is sort of that point, and then this is the difference between those. Yeah. Okay. How are we doing? Is everybody on board? Just for arithmetic sort of curiosity, value plus differential makes this our estimate. And then, just how well did we do? This linear approximation. Did do a good job of approximating the function. We'll whip out a calculator. This is the, to at least a few decimals, this is the right answer. Notice, by the way, I can't emphasize enough, these are all approximate, right? Even the calculator's calculation, that's an approximation. This is an irrational number that extends infinitely in the decimal. But nevertheless, pretty close, right? Definitely much better approximation than guessing, about 2. This almost nailed it. Oh, neato. Okay. All right. Okay, so this next page is this represents a bunch of compromises. There's a couple of weeks worth of discussion that I'd really like to make about what I squeezed onto this one page. We just can't cover all of that. There's just not enough time. But there are some ideas of definitions of things like what does it mean for a function to be continuously differentiable? That's actually an easy one. I'm totally going to talk about that. But the idea of what it means for a function to be differentiable is subtle and unexpectedly weird and unexpectedly hard. So we're not really we're going to pretty much kind of skip the definition of different. I'm going to write it down. I'm going to point to it, right? But I'm not going to be able to spend any time on, in this course on, what precisely does it mean for a function to be differentiable and why. And let me point out this is a weird, again, discrepancy between single variable calculus and multivariable calculus. In single variable calculus, differentiability is easy to define. Right? Function's differentiable if you can differentiate it. Right? It's the easiest definition in the world. And it turns out, again, hard discussion, but we just can't. It doesn't work that well in a multivariable context. Roughly speaking, with the additional dimensions to move around in the domain. There's just a lot of different ways in which things can happen weirdly that you just can't see in a Calc 1 context. So it's a wonderful discussion. It's very, very interesting. A lot of fun. I'm sad that we can't do it. But oh well. If you take Math 222 instead of Math 212, you'll see a lot more of that kind of thing. Okay. So we'll start with one thing that's easy that we can do, and that is the definition of what it means for a function to be continuously differentiable. It's really easy. It means exactly what you would expect based on ripping off from Calc 1. It means that partial derivatives, because this is a multivariable context, but the derivatives exist and are continuous. Right? Thus continuously differentiable. Exactly what you would expect. And here's another little bit of good news. Most functions that we're going to deal with are continuously differentiable. Vast majority of the functions that we're going to deal with are continuously differentiable. Here's some even better news, arguably. Every function that's continuously differentiable definitely is differentiable. That's fantastic. Right? So most of the time, everything that we're going to be interested in this course, the way to check if a function is differentiable is check and see if it's continuously differentiable, because it probably is. And once you check that it's continuously differentiable, you immediately know it's differentiable, and exactly what that means, exactly what differentiable means. We can't write that down. It's hard. But the point is, you can confirm it pretty directly. Okay, so it's a great trick. Make sure to understand this trick about continuous differentiability and how that implies differentiability. Now I'm going to say a couple of words, though, about what differentiable means. This is all going to have to be pretty ambiguous, but we've got this formula for linear approximations, and in a very important and meaningful sense, it means that the linear approximation gives you good approximations. And you'll note I put that in quotes because I'm not going to define what that means. But in a very reasonable way, it's just really hard to write down, but in a very reasonable way, that is what differentiable means, that the linear approximation gives you good approximations. Okay, all right. Here's a different way of saying the same thing. Keep in mind, the linear approximation formula was the function whose graph is the tangent plane. Well, so another way to say that same thing is that when you use your linear approximation to find your tangent plane, that this is in fact a good tangent plane. And now again, I have to sweep under the rug. What do I mean by good? Well, that's a whole long conversation, and there's some anomalous cases and weird, very counterintuitive, how could this possibly be scenarios. And y'all remember all that stuff with limits and how you can come from all different possible straight lines and the limit always gives you the same value? But if you come in along some curve, then all of a sudden you get something really unexpected that just by virtue of curving in, the limit is incompatibly different from all the different straight line directions. That's super weird. There are analogously weird little catastrophes that can happen when you're talking about differentiability. So there's a lot to say, and again, we just don't have the time. But anyway, here's how you write down these loose statements. We say a function's differentiable if there exists a vector c, which you stick here in this equation, and note that this is a multivariable limit. If you can find a c that makes this limit equal to 0, multivariable limit, cannot emphasize enough, then the function's differentiable. And why this is the expression that we should be looking at. It's a 20-minute discussion that we just don't have time for. So anyway, I need to have pointed this out, and I want you to be aware that differentiability is hard to define. Hard to define, but easy to confirm. All right, everybody on board? Any questions? Feel free. Okay. One last comment I'll make. Pretty reasonable question to ask at this point would be, okay, how about this? If this is such a complicated discussion, why don't we just jettison this concept entirely, differentiability is a weird thing to talk about, and this is easy. Let's just talk about continuous differentiability. Why not just write everything in terms of continuous differentiability? And sadly, there's a good answer to that question. There's a cost in using the stricter notion of continuous differentiability, and that is that there are some functions that are differentiable. They're not continuously differentiable, but they are differentiable. And there's a lot of theorems for which the right condition, the sharp condition that's necessary for the result to follow is merely differentiability. Right? So if you state your theorems that, look, I'm going to require continuous differentiability, then you're making unnecessary, as it turns out, unnecessary constraints, and you're inadvertently stating a weaker version of the theorem, and mathematicians hate that. So anyway, we can't get rid of it. It is unavoidably differentiability and not continuous differentiability. Differentiability is the right condition. It's the point relevant to a bunch of important theorems. So, all right. So that's all I have time to say about that, unfortunately. Okay, moving on. That was 13.6, by the way. Real quick. Partial derivatives is 13.4. All this stuff about differentiability and linear approximations was 13.6. What happened to 13.5, you might ask? I am skipping 13.5 for the moment. I will also be skipping 13.9 and 13.10 later on, a week or two, for reasons that are hard to explain right now. But those three sections are still part of the course. We're still going to do them. We're just going to do them after we finish chapter 15. There's a really good reason to take those three sections in particular and delay their discussion until after chapter 15. So 13.5, 13.9, and 13.10 you can just kind of forget about. For the moment, just don't worry about them. Just skip over them. And when we get to exam 2, they will not be fair game. Okay? They will not be fair game until midterm 3, and of course also the final exam. Okay. All right. Yeah.
So this exam is up to 13.3.
Let me not answer that question because I don't remember what I wrote in the email. Whatever I wrote in the email is the official answer, and I don't trust myself to remember. That's why I write things down. Yeah. So whatever the email says. Okay. The chain rule. Y'all remember the chain rule from Calc 1. Right? Again, make sure to brush up on that. Make sure that you are, proficient with the execution of the chain rule, and of course also the understanding of what it means and why. Okay. So it turns out that we can get a multivariable version of that without too much trouble. We're actually kind of already there, sort of. We already have this formula right here. This is a different notation, but this is our linear approximation formula. There's that differential. Keep in mind that basically says, L of x minus L of a. And here's, gradient dot dx. A different notation for it, but anyways, same idea. What we have here is a function that takes R2 to R1. The two input variables are x and y, and the output variable is z. All right, so that's our sort of context here. And now I pose the reasonable question of, let's suppose with z as a function of x and y, what if x and y were functions of yet another variable, t? Right, so I'm going to take this picture right here, where z is a function of x and y, and I'm going to precompose with x and y being functions of t. Right? Like free country, I can pretend x and y are functions of t. Right? And with that setup, I just take this equation here and just divide by dt, and look what we get. Right? Nothing to it. And what this says is I can understand the derivative of the composition. Oh, let's see here. The composition derivative of the composition is dz dt. Right? And I can understand that in terms of the partials of f. And, oh gosh, did I use the right I may have used my wrong colors. I'm sorry. And then the derivatives of x and y with respect to t. So this formula here, again, it's a straight, it's one step away from the linear approximation formula we already knew. With this formula, I have a connection between the derivative of a composition and the derivatives of the component functions. So, from that point of view, this is our first version of the chain rule. Okay, and it looks like I'm out of time, so we'll call it quits here today. And don't forget, we have a test on Wednesday. See you then. You've got an email from me about the content that's relevant. And let me also, while I'm here, there's some further discussion in that email that I sent out on Friday about the mechanics of the test. We're going to be using this thing called CrowdMark. As a result, it is required that you use black pen. Pencil is not okay. Another color is not okay. It's got to be black pen. Further details in that discussion. So make sure to bring a black pen, please. Let me stop this and you can come talk to me. Yeah, okay. See y'all later.
Oh, this is like...
Yeah.
I was saying, will you remind us, before the exam, to use black pen?
I hope I will. You're asking me to remember something, and that's a shaky, right? But I'll try.